Independent sets covers maximum bipartite matching. Recap of previous lecture. In previous lecture, we have discussed the concept of matching, perfect matching, maximal matching, maximum matchings, M alternating path, M augmenting path, symmetric difference, Hall's matching condition and vertex cover. In this lecture, we will discuss König-Egerváry theorem, that is for the connection between the maximum matching and vertex cover. We are going to also see independent sets, covers, for example edge cover, vertex cover, both kind of covers we will be including up. Maximum bipartite matching algorithms we are going to see in this lecture. One such algorithm, that is called augmenting path algorithm, we are going to cover up. Theorem, König-Egerváry theorem. The statement of the theorem says that if G is a bipartite graph, then the maximum size of matching in G equals the minimum size of the vertex cover. In the last lecture, we have discussed the implication of this particular theorem on a bipartite graph, and we have seen that in this particular figure, wherein the vertex cover is denoted by the green color vertices. Here the size of the vertex cover is 1, 2, 3, 4 in this figure, and the matching is represented as the red color, that is 3. So, vertex cover size is greater than or equal to here the maximum matching. So, matching basically now, so we are going to see this particular relationship between the vertex cover and the maximum matching in the condition when it reaches an optimum value. So, optimum value means the maximum size of the matching will equal to the minimum size of the vertex cover. So, that means Q is equal to M, and that condition when it arises, then the matching which is obtained will be the maximum matching. And so, basically if we are given with a minimum set of vertex cover of a graph, then we can identify the matching of a maximum size, and that is given by the König-Egerváry theorem. So, this particular theorem is also called min-max or a primal dual optimization problem, where maximization is in the terms of matching and minimize in the terms of vertex cover. So, using this particular condition, we will see the maximum matching algorithm which will utilize König-Egerváry theorem, or first we will see the proof, then we will see the algorithmic proof, that is called augmenting path algorithm, to find out the maximum matching in a graph. So, this particular theorem has two proofs. One proof we are going to give now, and after that the algorithm which we will discuss, that will be an algorithmic proof for this particular theorem. So, the theorem says that if G is bipartite graph, then maximum size of a matching in G equals the minimum size of the vertex cover. So, maximum size of a matching equals the minimum size of the vertex cover. Let us see the proof of this particular theorem. So, to prove this theorem, let us assume G to be a bipartite graph having a xy by graph or xy partition. Now, since the distinct vertices must be used to cover the edges of the matching, therefore, the size of the vertex cover denoted by capital Q cardinality is always greater than or equal to the maximum or equal to the matching, whenever Q is basically the vertex cover and M is the matching. Now, given the smallest size of the vertex cover, that means if we reduce the size of the vertex cover, that means we are going for this particular condition, it becomes equal. We construct a matching of size Q to prove the equality always be achieved. So, let us construct the matching if we are given the smallest vertex cover. We will partition the vertex cover which is given into two sets R and T. So, R will be in the partition X and T will be in the partition Y. Let us see in this particular figure. So, T is in the partition Y and this R will be in the partition X, and together T and R, they will basically form the total vertex cover. So, these are the vertices which are colored as red in T and blue in R, they will form the minimum vertex cover. Now, having partitioned into R and T, now then let H be the subgraph of G induced by R union Y minus T. So, R union means R and this becomes Y minus T. So, this part of the graph we call it as H. Similarly, H prime graph will basically also a bipartite, or it is induced subgraph of G, that is called as H prime, will have T union X minus T union X minus R. So, this becomes, this is R, so this becomes X minus R, this becomes T, so this becomes. So, we have now divided the graph into two subgraphs, one is called H, the other is called H prime, and now we are going to use the Hall's theorem to show that this H has a matching that saturates R into Y minus T, and also H prime has a matching that saturates T into X minus R. Now, since H and H prime they are disjoint subgraphs, the two matchings together form a matching of size Q in G. So, the matching in H and H prime together, if we combine, that will be the matching of size Q in the graph. That is how we are going to construct the matching. Now, let us see the next step. Since R union T is the vertex cover, so G has no edge which basically runs from Y minus T, that means from here, and X minus R, that means here. There is no edge which will go from Y minus T to X minus R. That particular condition is clear now. Why? Because R union T is a vertex cover. That means it will be covering all the vertices, so no more additional edges are required further to be included in that cover Q. Why? Because it is a minimum cover. Now, for each subset of R, here S is a subset of R, we consider the neighbor of this particular S which is contained in Y minus T, that we know. Now, if this particular neighborhood relation size is less than S, then what we will do, we can replace this particular neighborhood N of S for S in Q to obtain a smaller vertex cover. So, that is way we are going to construct a smaller or the smallest vertex cover which will satisfy NH of S, which is always at least, and hence we do this to satisfy the Hall's condition. Now, you know that Hall's condition will saturate this particular R through the matched edge. So, the minimality of Q thus yields the Hall's condition in H here, and hence H has a matching that saturates R. So, applying the same arguments in H prime, we will see that there exists a matching which will saturate T. So, R and T, they are basically being saturated in this particular construction, and hence this basically, once we identified this kind of vertex cover of a minimum size, then it will generate the maximum matching of that size Q that is shown over here, which will saturate R and T. Now, in this theorem we have seen the min max relation. So, minimization of a vertex cover will give you the maximum matching, and this is called min max relation, is a theorem stating equality between the answers to the minimization problem and the maximization problem over a class of instances. So, König-Egerváry theorem is such a relation for vertex cover and the matching in a bipartite graph. Now, consider a dual optimization problem as a maximization problem M and minimization problem N defined on some instances such that for every candidate solution M or to M and every candidate solution N, the value of M is less than or equal to the value of N. Often the value is cardinality, as when M is maximum matching and N is the minimum vertex cover. When M and N are dual problems, obtaining a candidate solution M and N that have the same values proves that M and N are optimal solution for that instance, and that we have seen in König-Egerváry theorem. These theorems are desirable because they save the work. So, our next objective is another such theorem for independent sets in the bipartite graph, independent sets and covers. So, independence number of a graph is the maximum size of independent set of the vertices, and independence number of a bipartite graph does not always equal to the size of the partite set. In this example, here both the partite sets are of size 3, but the independent set, if we see, are the 4 vertices. So, independent set size is 4, whereas the partite set is of size 3. Now, here we will see that what is the vertex cover. So, if we include this particular vertex and this particular vertex, it will cover all the edges of this particular graph. Hence, the vertex cover is vertex number 1 and vertex number 2, that is of size. So, we will see that no vertex cover covers 2 edges of a matching. Similarly, no edge contains 2 vertices of an independent set. For example, this particular edge will touch only one independent set. This particular independent set will be touched by another edge. This independent set is basically touched by another independent set. So, set of independent sets 3, 4, 5 and 6, they are touched by the different edges. Why? Because if there is an edge which also touches another set, another node in the set, independent set, then it will not be independent set. Why? Because there will be an edge which is connecting it. So, that means the number of nodes which are there in the independent set and that many number of edges are required to cover the size of the independent set. What about other edges? So, the other edges here in this particular example, this particular edge is not basically touched by, is not considered here, which is touching the independent set, but this particular edge will be touched by one of these edges which are there present to touch the independent set. So, similarly, no edge. So, this will yield another dual covering problem. So, these set of edges which will basically touch all the independent sets, they will form an cover which is called an edge cover. So, edge cover of a graph G is a set L of edges such that every vertex of G incident to some edge of G, some edge of L. So, in this particular example, let us say that this edge cover includes this edge, this edge, this edge and this edge. So, when we include all these 4 edges, what are they going to cover? They are going to touch all the vertices of a graph. So, let us see that this vertex, all the independent vertices are basically touched by the 4 edges. What about these 2 edges? They will be automatically be touched upon. Why? Because automatically be touched upon. Now, we will see why it is going to happen. So, this is called the edge cover. It is opposite to the vertex cover. So, vertex cover is the set of vertices which will touch all the edges, and here edge cover means the set of edges which will touch all the vertices called edge cover. So, edge cover is the set of edges in the graph and is represented by capital L. So, when there is a perfect matching means all the vertices on both the sides they are being saturated. Then if let us say the graph is having n vertices, so how many different, what is the size of the edge cover will be having n by 2 different edges which will give a perfect matching. So, with this we are going to give some definitions and some terms also which we are going to use in the further theorem. So, for optimal sizes of the set in the independent sets and covering problem, the following terms are defined. So, alpha G is nothing but the maximum size of independent set. So, this is the set of vertices. Then minimum size of the vertex cover, as I told you, is vertex cover is a set of vertices which will touch all the edges, it is also a vertices. Then the maximum size of the matching, here this is nothing but a set of edges, and a minimum size of the edge cover, this is also the set of edges. So, the edge cover problem is to minimize this particular set called minimum size of the edge cover. Vertex cover we also going to minimize, that is the minimum size of the vertex cover is important. Matching we always maximize, called maximum size of matching. Independent set also we are trying to maximize, called maximum size independent set. These will become the optimization problems, and let us see their solutions. Now, having stated these notations and definitions, let us again restate the König-Egerváry theorem. So, König-Egerváry theorem is the size of the maximum matching equal to the size of the minimum size of the vertex cover. So, beta indicates the minimum size of vertex cover and alpha prime G denotes the maximum matching. So, now König-Egerváry theorem we can write also in this particular manner. Let us say that this is equation number 1. Now, we will prove also that alpha G is equal to beta prime G. So, beta prime G is nothing but the edge cover, and this is the minimum size of the edge cover, and here alpha G is an independent set, the maximum size of independent set. Now, here we can see that no edge can cover 2 vertices of an independent set. So, take the example. This is one independent set, another independent set, this is another independent set, and one. So, for every independent set, for every node in the independent set, there will be an edge. So, how many edges will be there in the edge cover? At least that many number of edges will be there, that is beta prime g has at least alpha g number of edges in it. So, hence this particular equality basically is established. Now, there is a lemma which says that in a graph G, the subset of the vertices is an independent set if and only if the complement of that particular subset S is a vertex cover, and hence alpha g plus beta g is equal to the total nodes in a graph. So, proof, let us see. Now, if S is an independent set which is a subset of vertices, then every edge is incident to at least one vertex of S prime. So, let us see that these 4 are basically the independent set, and this vertex belongs to the complement of that independent set. So, it says that if S is an independent set, then every edge incident to at least one of S prime. So, you see that this particular edge which basically touches the independent set, it also touches S prime, one of these. Similarly, here also the same thing is happening. This edge is basically touching the independent set, also touches the complement, This also touches the complement. So, conversely, if S prime covers all the edges, S prime, these basically set of vertices which covers all the edges, then no edges joining the vertices of S, and hence they will becomes the independent set. Hence, every maximum independent set is the complement of the minimum vertex cover. So, here the vertex cover, we have to see that alpha g is basically the independent set and beta g is basically the, so this is basically the independent set plus this is the vertex cover. So, that becomes the total number of vertices in the graph, and that is what we are going to prove by this particular process. Now, in a graph G, the same things which we can see through the example. In this particular lemma, we can see that independent set size is 4, 1, 2, 3, 4, and the vertex cover size is 1 and 2. So, total if we sum them, alpha plus beta, that becomes n, and that is nothing but a 6. Hence, the relationship between the matching and the edge cover is more subtle. Now, nevertheless, the same formula holds. Now, we are going to see another theorem which says that if G is a graph without isolated vertices, then alpha prime G plus beta prime G is basically the total vertices of a graph. Alpha prime G is the maximum matching and beta prime G is the edge cover. This is the minimum size, this is the maximum matching, and now we are going to see the proof of this particular equation or a theorem. So, from a maximum matching n, we will construct an edge cover of size n minus m. Now, since the smallest edge cover is no bigger than this particular cover, so this will imply that beta prime G is at most n minus alpha prime G. So, again you can see that this particular inequality you have derived from the previous results. In the sense, we have seen the edge cover that is, let us say that it is beta prime g, and we have also seen that this edge cover is equal to the independent set. We have also seen that independent set plus vertex cover becomes the total number of vertices. So, that means the edge cover equal to n minus the set of vertex cover, and this vertex cover basically we can denote by beta. Now, this vertex cover is equal to the maximum size of the matching, so that becomes alpha g. So, hence beta g is less than alpha prime g, and hence this particular inequality is established. Now, we can also see from minimum vertex cover we can construct a matching, and that is quite obvious. That is, if the edge covers are given, then we can construct a matching of size n g minus 1. Since the largest matching is no smaller than this particular matching, hence this will imply that alpha prime g is at least n g minus beta g, beta prime g, where beta prime is basically the edge cover. Now, corollary, which says that if G is a bipartite graph having no isolated vertices, then alpha g is equal to the beta prime g. Alpha g is basically the maximum size of the independent set, and beta prime g is the minimum size of the edge cover. So, by previous lemma we have seen that alpha plus beta is equal to n. Also we have seen alpha plus alpha prime beta prime also is equal to n. So, from these lemma and from these two theorems we have got this. So, we can write down alpha plus beta is equal to alpha prime plus beta prime. Now, König-Egerváry theorem, in previous we have seen that alpha prime is equal to beta. Then what we are going to do is we can subtract alpha prime and beta from this particular equation. So, when we subtract, we will obtain alpha is equal to beta prime, and this basically is a corollary which will complete this proof. Now, maximum bipartite matching, maximum size of bipartite matching, that means the theorem König-Egerváry theorem states that maximum matching is achieved when there is a minimum size of the vertex cover also is achieved. Hence, its min max theorem we are going to use over here as a algorithmic proof. This algorithm we will see. So, to find the maximum matching, we iteratively seek for augmenting paths, and if we found the augmenting path, we can enlarge the current matching. So, in a bipartite graph, if we do not find augmenting path, then we stop at that point and we will conclude that we have found the vertex cover with the same size as the matching, and thereby proving the König-Egerváry theorem that the matching has of the maximum size. So, this yields both the algorithm to solve maximum matching problem and algorithmic proof for König-Egerváry theorem. So, we will see this is the first algorithmic proof in this course. Now, given a matching M in XY bigraph, we search for M augmenting path from M unsaturated vertex in X. We need only search from the vertices which are unsaturated in X, because every augmenting path has an odd length and thus has ends in both X and Y. We will search from unsaturated vertex in X simultaneously, starting with a matching of size 0, alpha prime g applications of augmenting path algorithm will produce the maximum matching. So, augmenting path algorithm input is XY bigraph, also input is the matching M in the graph is given and also the set U of M unsaturated vertices. The idea of this augmenting path algorithm is to explore M alternating path starting from unsaturated vertex U, letting S, which is a subset of the vertices X, and T, which is a subset of the vertices from Y, be the set of vertices which are reached by this M alternating path starting from U. Mark the vertices of S that have been explored for the path extension. As the vertices is reached, record the vertices from where it is reached, and let us see the initialization where S is initialized to U. That means initially all the vertices are unsaturated and T becomes empty. Why? Because we haven't visited any vertices. Now, the iteration of this algorithm, if S has no unmarked vertex, then we will stop and report T union X minus S as the minimum size of the vertex cover and M as the maximum matching. So, this is the termination condition of the algorithm. Otherwise, we have to select an unmarked vertex, let us say X, which belongs to S. To explore X, consider each Y which is a neighbor of X such that X Y is not in matching. So, it is nothing but, if you recall, it is basically to explore augmenting path starting from unsaturated node X. Now, if Y is unsaturated, then terminate and report an augmenting path from U to Y. Otherwise, Y is matched to some X by M. In this case, include Y in T reached from X and include W in S reached from Y. After exploring all such edges incident to X, mark X and iterate. Again, I am explaining. Let us see that this is the set of nodes out of S which are unsaturated. So, let us say that X belongs to U and which is unmarked. Now, we will take this is unmatched edge, we will take this edge and reach some of the node in Y, and let us call this Y which is a neighbor of X here, and this particular edge X Y should not be in the matched edge. So, the matching which is shown as the red color, it is not one of them. So, we can reach from X to Y via unmatched edge. Now, if Y is unsaturated, now here it is saturated, Y is matched to some W which is there in X, let us say this is W, and it will reach through a matched edge to a W. This is not a possibility. Why? Because this is not a matched edge. So, in this case include Y in T. So, T will be including these particular nodes which is reached from X, and include W also into S, and so on we will explore. Now, if we reach to a unsaturated vertex here, that means if you start in the beginning it will be unsaturated, then Y will be, then we have identified the augmenting path and we terminate this particular augmenting path algorithm. So, we have to basically call this augmenting path algorithm how many times, that we are going to see in this particular example. So, if let us say that in the beginning we are given X Y by graph, X contains the nodes which are labeled as 1, 2, 3, 4, 5, 6, Y contains A, B, C, D, E, F. Now, initially there is no matching. So, M is initialized to empty and all the vertices of X are in U, that is all are unmarked and unsaturated. Now, we will select one vertex from U, let us say it is vertex V1. Now, consider the neighbor of V1 which is basically unsaturated. When we reach to a vertex A, this also is unsaturated. So, hence this particular V1 VA is an augmenting path, and this algorithm will be terminated, and then again we will include this particular edge in the matching and also we will modify u. Why? Because 1 will be removed from the current u. So, it will be now 2, 3, 4, 5, 6. So, we will continue doing this. Let us see that we reach to a stage where the matching has reached 4 different edges, 1, 2, 3, 4, which are shown as the bold, and let us say u is having 4 and 6, which is unsaturated. Now, we will select one vertex from u. Let us assume we have selected 4 and we call it as V4. Now, if we see the neighbors of 4, there are only 2 neighbors, one is A, the other is C. So, these A and C, they are saturated, they are not saturated. So, neither of them are unsaturated. So, we mark VA and VC, they are reached. Then consider the mate of VA and the mate of VC, that means via a matched edge we can reach to 1. Similarly, from C using matched edge we can reach to 2, and we have to write down from where we are reaching to these vertices of X, and that will be. Now, consider the neighbors of V2, this is V2, which are VA and VC. So, either VC or VA, they are already reached. So, nothing new will be explored further from this V2. Now, we will see the neighbors of V1. So, the neighbors of V1 is A, we have already explored, and B, where B is unsaturated. Hence, we have identified starting from unsaturated vertex and we have reached to an unsaturated vertex, and that is called an augmenting path. So, if we trace this augmenting path which we have identified like this, we started from V4, then we have reached to VA, and from VA we have reached to V1, and from V1 we have reached to. So, this is an augmenting path which is shown as the green color, and once the augmenting path is identified, then the algorithm terminates, and then as far as the matching is concerned, we have to modify the matching so that the next iteration will begin. So, now we will mark 4 as the node which is now is saturated. So, it will be out of this box. So, only the unsaturated node remains is 6. As far as the matching is concerned, so now we can see that we have to modify this particular matching paths. So, that means the earlier was 1 and A, that particular path will be removed. Why? Because this will no longer be in a matching, and a new particular edge 1B, this particular edge will be included. Similarly, another edge which will be included is 4A, this edge. So, again if you recall, so 1B is this edge and 4A, this edge is included, and what are the other edges which are there is 2C, which were there in earlier. So, now in this particular new figure we can see that 1B is added and 4A is added in the matching, and this particular path which starts from V4, that means this particular node is saturated. Why? Because it has a matched edge. It will go to A, that also is the saturated node, then it will go to 1 via unsaturated. So, it was there earlier, so now it has to be removed from M. So, it will become unsaturated edge. Then again we have to include this edge. Why? Because this will be a matched edge, that is from 1 to B, that we have included. So, we start from unsaturated node here and we have reached to unsaturated node here, that is fully explained here in this particular example. Now, in the last when we have only the remaining unsaturated node, that is node number 6, and this is the matching which is given and shown here in the dark colored, and S is basically this set of vertices which is saturated by these particular edges. So, since 6 cannot be included, why? Because we cannot find an augmenting path. So, here we terminate. When we terminate, the vertex cover will be T union x minus S. So, what is T? This is T. And what is S? S is 1, 2, 3, 4 and 6. 6 also will be there. Why? Because there will be a path which will be identified. So, we will terminate, then that means all the nodes which are there in T, that will be included, and then x minus S, that means the nodes which are there in 1, 2, 3, 4, 6, 1, 2, 3, 4, 6 is also saturated, will be included. X minus S will become 5, so 5 will be included, so that will become the vertex cover. So, vertex cover is 1, 2, 3, 4, 5, different size of the vertex cover is 5. So, we have to find out, we have also identified a matching of size 5. So, this is 1, 2, 3, 4, 5. So, when the algorithm terminates, we have already identified the 5 different matched edges. So, let us see the proof of this particular theorem. Theorem says that repeatedly applying the augmenting path algorithm to a bipartite graph will produce a matching and a vertex cover of equal size. Let us see the proof. So, we need only to verify that the augmenting path algorithm produces an augmenting path or a vertex cover of size m, because every iteration is doing this. So, if the algorithm produces augmenting path, then we are finished. Otherwise, it terminates by marking all the vertices of S and claiming that Q is a vertex cover is T union x minus S is the vertex cover of size m. So, we must prove that Q is a vertex cover and has size m. To show that the Q is a vertex cover, it suffices to show that there is no edge which is joining S and y minus t, that we have already seen figures. An alternating path from U enters X only on an edge in the matched edge. Hence, every vertex of X of S minus U is matched via M to a vertex of T, and there is no edge of M from S to y minus t. Also, there is no such edge outside M when a path reaches X. It can continue along any edge not in M, and exploring X puts all other neighbors of X into T. That means we are tracing back the augmenting path. So, whatever nodes we are reaching, we basically will form S and T, those set of vertices as the vertex cover, and also we are forming the edges which are matched. So, now we study the size of Q. So, algorithm puts only the saturated vertices in T. So, each y which is there in T is matched via M to a vertex of S, hence U is a subset of S. Also, each vertex of S minus X is saturated, and the edges of M is incident to X minus S cannot involve T, hence they are different from the edges saturating T, and we find M has at least T plus X minus S edges. Since there is no matching large than this vertex cover, so we have concluded that the cardinality of M is equal to cardinality of T plus cardinality of X minus S, that is nothing but a Q. So, here we have seen that if a bigraph is given with a n vertices and m edges, now since alpha prime g, that is the maximum size of the matching, is always less than n by 2. Why? Because if it is a perfect matching, we have earlier seen that the size of the perfect matching will be n by 2 if n different vertices are there. So, we find a maximum matching in G by applying this augmenting path algorithm how many times? N by 2 times. So, each application explores a vertex of S at most once just before marking it, thus it considers each edge at most once. So, if the time for one edge exploration is bounded by a constant time, then the algorithm to find out the maximum matching by calling augmenting path algorithm n by 2 times, total time will be order of n times m to find out maximum matching using augmenting path algorithm. There is another algorithm given by Hofcraft and Karp algorithm. This is the faster version of the algorithm which runs in a quicker time, that is of the order root n of m, which is the value which is less than this particular time. So, we will see this algorithm in later classes. Conclusion: in this lecture we have discussed König-Egerváry theorem, independent sets, covers, that is edge cover, vertex cover, maximum bipartite matching and augmenting path algorithm. The coming lectures we will discuss weighted bipartite matching, stable matching and a faster bipartite matching algorithms. Thank you.